A titration is an experiment where acid or base is added to base or acid respectively. It is a neutralization reaction because if we start with sodium hydroxide base in the conical flask, for example, then we will see a decrease in pH as the acid is added. This eventually gives us a neutral solution. We can detect the pH change using an indicator such as litmus paper or universal. Universal indicator is a continuous indicator as the colour gradually changes through depending on the pH level. Litmus paper and other indicators such as phenolphthalein will just show a colour change from one colour to another colour upon neutralisation. Supposing we have acid HCl in the burette, we will find that exactly n moles of HCl will neutralise n moles of NaOH. This can be seen by writing out the equation of the acid-base titration. 1 mole of HCl reacts with 1 mole of NaOH to give 1 mole of H2O and 1 mole of NaCl salt. But we could have 2 moles of HCl with 2 moles of sodium hydroxide, giving 2 moles of water and 2 moles of salt. We could have 3.65 mole, and etc, etc, etc. So we generalise that to n mole of HCl will react with n mole of NaOH. But how would we do this practically, and what calculations might be involved? Starting with the solution in the conical flask, sodium hydroxide is usually a powder of white crystals. To prepare our sample in the conical flask, we must dissolve sodium hydroxide and form a solution. This solution will have concentration C2 and volume V2. Normally, for a titration, we fix the volume in the conical flask at 25 centimeters cubed. Now, going to the acid in the burette, it will be a liquid and we can just pour it into the burette as and when necessary. This will have concentration C1, we'll have a volume V1. I'm going to define V1 not as the total volume of HCl in the burette, but the total volume of HCl that gets added to the NaOH solution to neutralise it and cause the pH to be 7. This volume is the mean titer. Normally you'll be given a table of volumes in centimetres cubed of the rough and several regions of the titer. Titer values that we include in our answer must be within 0.05 centimetre cubed of one another. If there are any that are significantly higher or significantly lower, we must discard those values as they are erroneous results or anomalous results. Remember, when calculating the mean, you should always divide by the number of values that you are averaging over. So if we were having A and B, their average would be A plus B over 2. Normally, the mean titer is around 19 centimeters cubed. A typical concentration would be 0.15 mole per decimeter cubed. From these values, we can work out that the number of moles of HCl added to the NaOH solution is concentration times volume over 1,000. Written explicitly, we can see that subbing in the numbers gives us 0.00285 mole. Notice how the answer is quoted to 3 significant figures, and also this is a very small number. The number of moles is normally less than 1, and even has 2 zeros maybe after the decimal point. When it comes to the number of moles of NaOH solution, we don't know the concentration. Well, we might, but in most questions, such as the one that I was basing this video off, the C2 concentration is unknown. That means that we cannot work out the number of moles from C2 times V2 over 1,000. However, we know that in a titration, the 1-to-1 ratio of NaOH and HCl means that the number of moles of NaOH is equal to the number of moles of HCl. We just calculated the number of moles of HCl to be this number here. That means that this is also the number of moles of NaOH. If N equals C times V over 1,000, which for NaOH will be C2 times V2 over 1,000, we can rearrange this equation to find a value for C2. To show this explicitly, we take the 1,000 over to the other side. This means it has to be timed. If we bring that 25 underneath, that means it has to be divided. Therefore, we end up with an expression for C2. Subbing in these numbers, we have C2 concentration of 0.114 mole per decimeter cubed, which is exactly in the region that we'd expect for a concentration. Concentrations are normally 0.15, 0.1, around that. 0.2 maybe, if you've got very high concentration, but here is a very good answer for that question. So now we have the concentration of our solution of NaOH that was in the bottom of the conical flask. The units are mole per decimeter cubed. In the question, we were told to work out the mass of sodium hydroxide that we had originally in our powder, and that the units that we had originally in our powder, and that the units of that are grams. What I forgot to say at the beginning was that normally we dissolve our NaOH in solution and make up a stock solution. Then we take a sample of the stock solution to go into our conical flask, and that sample is always 25 centimeters cubed in volume. Our stock solution may be 200 centimeters cubed in volume, perhaps. But the thing that is consistent is that the concentration of the stock solution is the same as the concentration of the volume that is in the conical flask. That means that we can say that the stock solution has concentration 0.114 mole per decimeter cubed. Knowing this, we can work out how much NaOH was added to this to make the stock solution. First, we need to find out the number of moles that we had in the stock solution. That will be equal to the concentration times the volume. In this case, the volume is 200, but the concentration is the same as before. We need to divide by 1,000 because our unit for volume is in centimeter cubed. Then we will end up with a value of 0.0228 mole. However, we still haven't got our mass in grams. If we want to go from moles to grams, we can use our equation. Number of moles is equal to mass over molar mass. However, we need to rearrange it so that mass is the subject of the equation, the thing on the left-hand side. Mass always has to be on the top. It's the biggest. So we have to times two smaller numbers together to make the mass in grams. We know the number of moles, it's here, but what's the molar mass? Well, the molar mass of NaOH is simply 23 plus 16 plus 1 grams per mole. Because we've added the relative atomic mass of sodium, oxygen and hydrogen together to get the relative molecular mass, and that comes to 40 grams per mole. Therefore, our final calculation can be written 0.0228 mole times 40 grams per mole. We see that the moles cancel, which leaves us with grams as the units, and the number we want is 0.912. Note how we're giving the answer to three significant figures, that's an S there, and this seems like a reasonable mass of sodium hydroxide to be adding. The titration calculation gets more complicated if we don't have a one-to-one ratio. For example, when we react sodium hydroxide with H2SO4, we form water and Na2SO4. However, this is not a balanced equation. Over this side there are 3 hydrogens, but this side there are only 2. To balance this equation, we need to add 2's in front of the NaOH and H2O. This means that we end up with a 2-to-1 ratio of sodium hydroxide to H2SO4. If we imagine our setup again, we have sodium hydroxide in our conical flask and H2SO4 as the acid in our burette. We can calculate the number of moles of H2SO4 by using the volume from the titer, the mean titer V1, and the concentration will be on the bottle of the H2SO4 acid, but you should be told this in the question. Let's sub some numbers into it using exactly the same numbers as before. Again, we end up with this very small number of moles of H2SO4. And unlike before, the number of moles of H2SO4 is not equal to the number of moles of NaOH. In fact, we can see from this equation that the number of moles of H2SO4 is always half of the number of moles of NaOH. So you should always look at the equation and go, okay, number of moles of H2SO4 is equal to half the number of moles of NaOH. This actually means that the number of moles of NaOH is equal to 2 times the number of moles of H2SO4. There I've just rearranged, I've taken the 2 to the other side, and then it becomes timesing, multiplying rather than dividing. There I've just rearranged, I've taken the 2 to the other side, and then it becomes timesing, multiplying rather than dividing. Subbing in our number of moles of H2SO4, we can say that the number of moles of NaOH is equal to 0.000570. Now let's just check in our heads, does that make sense? Yes, it does, because we have a 2-to-1 ratio of NaOH to H2SO4. We have 0.00570 and 0.00285. And I would always write it out with the chemicals like this, and write out the ratio from the equation, and write out the numbers, so that you know that you've got the NaOH on the correct side, and the correct one is bigger than the other one. Writing this out a bit more neatly, we have number of moles of NaOH equals 2 times 0.00285, which is equal to 0.00570 mole. So now that we know the number of moles of NaOH in the bottom, we can find the concentration, which was unknown. So we knew V2, but we wanted to find C2. Oops. So C2 can be found by doing the calculation as before. But now we have a much higher concentration. In fact, the concentration is double, so we have a concentration of 0.228 mole per decimeter cubed. That was the concentration in the conical flask, but we know that it's exactly the same concentration in that sample that we had originally. The stock solution that we had has the same concentration, C2, but it has a much larger volume of 200. Normally, like you'll be told in the question, the volume of the stock, and it's normally around 200 or 250, so the concentration of the stock is the same as C2, and the volume of the stock is different, it's 200 centimeters cubed. That means that we can work out the number of moles of in the stock solution to be 0.0456 mole. That's not quite a grams, so again we have to use our number of moles is equal to mass over molar mass, and we rearrange this to give us mass is equal to number of moles times molar mass, and the number of moles we just worked out to be 0.0456 mole. The molar mass again is 40 grams per mole, and that will give us 1.824 grams, which is 1.82 grams to 3 significant figures.